Let's talk about light. We flip a switch and it's there, it lets us see everything. But what is it really? I mean, what is it made of? For centuries, that one simple question started one of the biggest, most epic debates in the history of science. Today, we're going to pull back the curtain on the secret life of light. So here's the central mystery. Is light a stream of tiny little bullets, these little particles of energy? Or is it a wave, something that flows and ripples through space like waves in the ocean? For the longest time, science was completely divided on this. And trust me, this wasn't just some friendly academic argument. It was a battle for the future of physics itself. So let's get into it. The great debate. Particle versus wave. The answer to this, it turns out, would completely change how we understand the universe. Okay, so in one corner, we have the absolute heavyweight champion of physics, Sir Isaac Newton. His idea, the corpuscular theory, basically said light is made of tiny particles, or corpuscles. But in the other corner, you've got Christiaan Huygens, who came along and said, nope, you're all wrong. Light isn't a particle at all, it's a wave. You've got two of the most brilliant minds on the planet with two completely opposite theories. So who was right? Huygens' wave theory was actually pretty beautiful. He came up with this idea called Huygens Principle. Just imagine a wave moving forward. He said that every single point on the edge of that wave acts like a tiny new source, sending out its own little mini wave, which he called a wavelet. All these little wavelets then expand and merge together to form the next big wavefront. So let's just walk through that real quick. You start with your main wave. Then every point on it sparks its own tiny ripple, a secondary wavelet. The new wave is just the line that connects the outermost edges of all those little ripples. It's a really elegant way to explain how a wave actually moves and propagates through space. Now, for more than 100 years, this was all just theory, a debate. But then, one scientist came up with a single, absolutely brilliant experiment that would finally give us the proof we needed. It was an experiment for the ages. And the key, the smoking gun, was a phenomenon called interference. See, here's the thing about interference. Particles just don't do it. If you throw two marbles at each other, they just bounce off. But waves, oh man, when waves run into each other, they do something completely different. Something kind of magical. Interference is basically what happens when two waves occupy the same space at the same time. They can either add up and become stronger, or they can literally cancel each other out, creating nothing. It's like if two people hum the exact same note. They can get louder together, or if they're perfectly out of sync, they can create silence. And this leads to two outcomes. When the crest of one wave lines up with the crest of another, they build on each other. That's constructive interference. And for light, that means a bright spot. But if the crest of one wave lines up with the trough of another, they cancel out. That's destructive interference. And that gives you a dark spot, absolute nothingness. Which brings us to Thomas Young and his now famous double-slit experiment. The setup couldn't be simpler. You just shine a single light source at a wall with two tiny parallel slits cut into it. And then you just look at the pattern that shows up on a screen behind the wall. Simple, right? Well, the result was absolutely mind-blowing. If light was a particle, like Newton thought, you'd just get two bright lines on the screen, right? One for each slit. But that's not what happened. Instead, Young saw a whole series of alternating bright and dark bands. That pattern could only be created by waves passing through both slits at the same time and interfering with themselves on the other side. This was it. This was the proof. Light behaves as a wave. Okay, so once the wave nature of light was settled, scientists started discovering it had a bunch of other superpowers, you could say, other behaviors that are also unique to waves. So first up, you've got diffraction. This is just the natural tendency for a wave to bend and spread out a little bit as it goes around a corner or through a small opening. You know how you can hear someone talking from around a corner? That's because sound waves diffract. Well, it turns out light does the exact same thing.
And then there's this really cool one, polarization. Okay, picture this. You're shaking a long rope up and down, making a wave. Now imagine you try to pass that wave through a picket fence. Only the up and down vibrations will make it through, right? The side-to-side ones will get blocked. Well, that's exactly what polarization is for light. It's like a filter that only lets light waves vibrating in one specific direction pass through.
And honestly, this is a huge deal. The fact that you can even polarize light tells us something incredibly important. It proves that light is a transverse wave. That just means its vibrations go up and down or side to side, perpendicular to the direction the wave is actually traveling. This was yet another piece of evidence that the simple particle theory just couldn't explain. All right, so this isn't just a bunch of dusty old physics experiments. Understanding that light is a wave is fundamental to the world you and I live in ways you probably don't even think about. Have you ever seen those beautiful, shimmering rainbow colors on a soap bubble or the back of a CD? That's interference and diffraction in action. You know those fancy sunglasses that cut down glare from the road or water? They use polarization. Even the fiber optic cables that bring the internet to your house work because of the wave properties of light. It is literally everywhere.
So, really, the big takeaway here is this. Figuring out that light is a wave wasn't just about settling an old scientific debate. It was the key that unlocked a whole new universe of technology, from modern communication to powerful telescopes that let us see to the edge of the universe.
So there you have it. The evidence is overwhelming. The debate is over. Light is a wave. Case closed, right? Well, here's the thing. What about those other times when light behaves, well, exactly like a particle? And that is where the story gets really, really weird, and it opens up the door to the wild world of quantum mechanics. But that's a story for another time.